Welcome back to ECE 501B. Homework number 7 is due this evening at 11:59. Let me know if I have the times or dates wrong. Someone in my other class said that I had shorted them 11 hours. I'd made it 12:59 instead of 11:59 for one of their assignments. So I gave them back. I gave them an extension of 11 hours. So they should be very appreciative of that. But I think the times are okay. Homework 8 and your deliverables, the last 2 deliverables for your project, are due a week from today. A week from today is our last time we will meet in class. That's the last day of class. And the next 2 lectures we will be talking about the second textbook of the class. So we'll cover chapter 10 today, and then we'll cover all of the 10 chapters of that next book in 2 days of next week. Now, we'll just try to set the stage and show the connection between finite dimensional vector spaces and infinite dimensional vector spaces, or functional analysis, in the next 2 lectures. Today, I actually want to do, and teacher course evaluations are also due in a week. I'm assuming you're getting daily or weekly reminders to complete those. I think they stop if you complete that. So there's a couple of ways to make those stop. One is to fill out the survey, and the other one is to wait until the 8th, and I hope you don't wait until the 8th. I hope you complete it before the 7th. The final exam is 2 weeks from yesterday, so it's the 13th. That's a Tuesday, and it will be at 6 to 8 p.m. Today what I want to do is not only cover 2 pieces of Chapter 10, but also talk about principal component analysis, and the Moore-Penrose pseudo-inverse. Those are actually 2 topics that are covered in some of our course resources. I may not get very far in PCA, and I may provide you with an additional sort of lecture piece for that in terms of notes and video for the PCA. And as I said before, we will step into the second textbook, which is functional analysis, where we're now doing signal space or function space types of ideas, and we'll try to motivate that with convolution and Fourier analysis, 2 things that I'm hoping you've seen before, and now you can make this connection from finite dimensional to infinite dimensional using concepts that you've already become familiar with. That's the idea. But today we're going to finish up the first text of trace and determinant, and then we'll talk about a pseudo-inverse, which we can relate to concepts we've already talked about, and principal component analysis also can be related to what we've talked about so far this semester. In Chapter 10, what we want to do is finally get into linear algebra done right, which means put off talking about the determinant until after we've touched on just about everything else in the course as far as finite dimensional vector spaces. Here, what we want to talk about are the trace and determinant of an operator. If we're dealing in a complex vector space, if V is a complex vector space, and T is a linear operator on that complex vector space, then the characteristic polynomial I think we talked about that last time at the end, of this operator T is given by this product of factors associated with our eigenvalues, and the factors are raised to the multiplicity of that particular eigenvalue. The characteristic polynomial then is Q of Z is equal to z minus lambda sub 1 raised to its multiplicity power d sub 1, z minus lambda sub 2 raised to the d sub 2, and d sub 1 and d sub 2 could just be 1. It depends on if these eigenvalues are repeated or not. And then we go on down to z minus lambda sub m raised to the d sub m. That characteristic polynomial then can be now written in terms of our linear operator, or we can apply that polynomial structure to our linear operator and say q of t is now, and if we now have an n-dimensional complex vector space, we will actually have z to the n in the polynomial, but that now translates into or leads to the operator t raised to the nth power minus a sum that now takes into account multiplicities, meaning if lambda sub 2 is repeated 3 times, we would have lambda sub 2 plus lambda sub 2 plus lambda sub 2 in this expression. We're taking all n eigenvectors, lambda sub n, times t to the n minus 1 plus dot 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 plus minus 1 to the n times the product of eigenvalues, and again multiplicities are included in this product, and in fact what we can now relate to this expression is the fact that this sum of eigenvalues is the same as the trace of our linear operator t, and this product of eigenvalues is equal to the determinant of t. And if we simply wanted one way to think about the trace and the determinant, chapter 10, we would be done just with this statement. But let's look a little bit more into that and try to get a better feel for what's going on, or how we can think of these two different topics. What if we looked at just a second order polynomial or characteristic polynomial? Let's say that we now have two eigenvalues, lambda sub 1 and lambda sub 2. This now can be multiplied out to give us the z squared, there's the z to the n, minus lambda sub 1 plus lambda sub 2 as scalars in front of the linear factor of z, plus the product of lambda 1 and lambda 2. So that is a very simple example for a characteristic polynomial, and if you now had a linear operator with eigenvalues lambda 1 and lambda sub 2, you could now use this expression to find q of capital T. And you now can see that the trace also is just made up of the sum of the eigenvalues, and the determinant is the product of those times, well, the product of lambda sub 1 and lambda sub 2 in this particular example. An abbreviation for the trace, I might say TR of T, and that's now this sum from I equal 1 to n of lambda sub I, where this sum of eigenvalues includes multiplicities. And now we might want to know, how do we compute the trace of t if we just start with the operator t? Maybe we haven't found the eigenvalues, or is there another way to think about the trace of t without having to compute or determine the eigenvalues of that operator? if we have the matrix representation of that operator, then we can actually find the trace of that operator. Trace of T is now the same or equal to the sum of the diagonal elements in that matrix representation of T. Or we now have the sum from I equal 1 to n. Again, we're in an n-dimensional complex vector space. We would just identify the n diagonal entries and sum those up, and that's equal to the trace of that linear operator. Relating this now to matrices, or just to think in terms of matrix facts, we can say that the following way. We can say our trace of a matrix A is now just the sum from I equal 1 to n of A sub II. And again, that's equal to the sum from I equal 1 to n of the n eigenvalues. Maybe I'll change the index so that it's not confused with I, but now if we went from L equal 1 to n, that also would give us the trace of that matrix. And again, multiplicities would be included in those n lambda sub L's in the sum. The determinant of a matrix, a lot of times we will just denote by a single vertical bar on either side of the matrix, or we might say determinant of A is now equal to the product from L equal 1 to n of lambda sub L. Where here for T, a linear operator on that vector space, complex vector space V, the determinant of T which we might denote det of T, is the constant term in the characteristic polynomial times minus 1 raised to the dimension of that vector space V, is the constant term in the characteristic polynomial multiplied by minus 1 raised to the dimension of that complex vector space V. Where if we now have complex vector space, the determinant of T, these eigenvalues lambda could be complex, and again we just simply take the product of those, where that product includes multiplicities. Now we can, because of that, we can write down some pretty quick propositions or theorems related to determinants and properties of those maps. One is proposition 24 in chapter 10, and that says an operator is invertible if and only if the determinant of that operator T is not equal to 0. can compute the determinant of that operator, and it's not equal to 0. It could be negative, it could be positive, it just has to not equal 0, then we know it has an inverse. And the proof of that is really just remembering, well, we could just remember the expression that we just derived. Remember, an operator is non-invertible if and only if it has a 0 for an eigenvalue. We had that statement earlier in the class. If we had a 0 eigenvalue, then we knew our operator was non-invertible. And in either case, or in both the complex and real case, the determinant of T involves this product of eigenvalues. Thus, the determinant of T is equal to 0 if and only if there exists a 0 eigenvalue lambda. So Proposition 24 simply says if you want to know can this operator be inverted, instead of directly trying to invert it, you can now compute the determinant, and if you obtain a non-zero determinant, you know that you can invert that operator. And maybe you don't want to invert it formally, you just want to know, is it possible in this particular scenario to invert that? Another observation or fact is as follows. For a linear operator T on this complex vector space and lambda and z belonging to that field, lambda is an eigenvalue of T if and only if the factor z minus lambda is an eigenvalue of the operator zi minus t. And with this fact, we'll be able to then say something more about how to compute the characteristic polynomial of a linear operator T. But here we're saying if we have an eigenvalue of T that's equal to lambda, then we know that this factor z minus lambda is also an eigenvalue of the operator zi minus t, where z is this variable. Where is that coming from? And really that's coming from just looking at this expression zv minus tv, or operating on the right with v of z minus t. We can, without any consequence, put an identity matrix or operator in between the scalar z and the vector v minus tv. But if v is an eigenvalue, if v is an eigenvector of t, then we can also write that as lambda v, where lambda is the eigenvalue. Here I'm saying that v is an eigenvector of T, and that's what we're assuming. And now we can actually rewrite this expression. We can factor V out of the right and have Zi minus T times V. And if we simply remove this identity operator, we can now factor Z minus lambda out of the vector V. But what does this expression what is that expression or that equation? If you simply look at what's in parentheses on the left as an operator and what's in parentheses on the right as a scalar, that has a very familiar form to it. That's simply our eigenvalue eigenvector equation. So this is now the eigenvalue eigenvector equation. And that's true if V is an eigenvector of the operator T. So if V is an eigenvector of T and lambda is its eigenvalue, then we can see that the operator Zi minus T has an eigenvalue Z minus lambda. And that's now going to allow us to write down another expression for or find the characteristic polynomial a different way. The above fact lets us compute the characteristic polynomial of T via the following theorem. Which is theorem 1025. If we have a linear operator T on a complex vector space V, the characteristic polynomial of that operator T equals the determinant of Zi minus T. So now we wouldn't have to find the eigenvalues of this linear operator T. We can just compute the determinant of this operator Zi minus T, where Z is now a scalar. And the way of showing that is going to rely on the previous fact. If we look at the determinant of T, we said that could be found by simply forming the product of the eigenvalues of T. So here we can say that the eigenvalues of the matrix representation of T equaling A, those are the eigenvalues of A. But now, if we simply use that same expression where our operator is no longer T, but it's Zi minus T, then we know that Zi minus T as an operator has eigenvalues of Z minus lambda for each lambda, and so now we can form our characteristic polynomial from that. Because now we can say that the determinant of Zi minus T is equal to the product of the eigenvalues of the operator Zi minus T, but we just showed above that the eigenvalues of the operator zi minus t are these scalars z minus lambda sub I, but this now, if we multiply it out, is z minus lambda 1 explicitly incorporating multiplicities where they exist. That now looks exactly like what we had before. As our expression for the characteristic polynomial. Or if we want to now find the characteristic polynomial of a linear operator, we can compute the determinant of this new map zi minus t without having to explicitly find the eigenvalues of that linear operator. That was just a part of this proof. But all we have to do to find the characteristic polynomial is evaluate the determinant of zi minus t. Questions on that? Pardon? You would love an example. Well, I don't have an example, so let's try to love on an example right now. Meaning, if we now had a linear map T that was, let's say, two-dimensional, then we could say, what do we want that linear map to be? So now we need it to be something in terms of a linear map, correct? So let's just say that the first coordinate is z1 plus 3z sub 2, and maybe the second coordinate is minus z sub 1 plus 4 z sub 2. Is that okay? Now, what's the matrix representation of T? Let's call it A. There's our matrix representation of T. And we now want to do what? Well, I'm going to now say that if I find the determinant of zi minus a, that will actually give me the characteristic polynomial of this linear map. So that now if I have zi, and if I subtract a from that, then I really am looking at z minus 1, minus 3, plus 1, and z minus 4 as my matrix that has this variable z in it, and now I simply need to find the determinant of that, and that's not that difficult for a 2 by 2. I now have the product of the diagonals minus the product of the off diagonals, or I now have z squared minus 5z plus 4 plus 3, or z squared minus 5z plus 7. And that's now the characteristic polynomial of that particular linear map T that we just created. And now if you wanted to, you could actually find the eigenvalues of that operator by finding the roots of this quadratic. We didn't have to find the roots of that quadratic to create this characteristic polynomial. But now we could if we wanted to. And can that now be factored very cleanly from that created linear operator? What are the eigenvalues here? Do we have them? No, it's not clean, is it? This doesn't factor nicely because we have this prime number in our constant, and that just has a 1 and a 7 as its factors, and they don't somehow magically combine to create 5. So now we would need to use the quadratic formula to find those eigenvalues. We would have complex roots in this cooked up example, but we could then find the characteristic polynomial by saying z minus lambda 1 times z minus lambda 1 star, and it should give us back that particular quadratic expression or quadratic polynomial, which is the characteristic polynomial. And maybe I'll let you do that on your own. But what else do you know about this particular polynomial? If this is now q of z, what happens if we look at q of a? Not u of a, q of a. If I now did this, what do you know that's going to equal? The A matrix needs to satisfy its own characteristic polynomial, which is the Cayley-Hamilton theorem. So if you needed to find an expression for, this is a easy way or a quick way to maybe find different powers of A, you now know that A squared is equal to 5A minus 7I from that expression. Or you could even find, if you multiplied this through by A inverse, for example, if it had an inverse, then, and it will in this particular case, then you could find an expression for A inverse in terms of powers of A. Another way of finding A inverse if it exists. Questions on that? That's now, and what's the trace of A? It's just 5. And what does that make sense with respect to what we now know? We know that this piece right here needs to be lambda 1 plus lambda 2. So we now know that this is lambda 1 plus lambda 2. What else do we know? What do we know about 7? We know that too, right? So we could find the eigenvalues of this without having to compute or go through the quadratic formula from our characteristic polynomial. We could solve it as 2 equations in 2 unknowns. We know now that lambda 1, lambda 2 is equal to 7. Another way of playing. So now you have plenty of games that you can play at home at your own convenience and entertainment, as long as you have some paper and pencil, right? To find eigenvalues, eigenvectors, trace, and different ways of connecting these concepts of linear maps. And now we went from this generic linear map that we simply cooked up to a way to relate or find its characteristic polynomial, and also a way to think about a relationship on its eigenvalues, which is a lot of times the more conventional way that you might see linear algebra approached, is you start with the determinant of this matrix and start finding eigenvalues and eigenvalues from that characteristic polynomial. We didn't do that. We started by finding these relationships of equations in terms of lambda from our eigenvector eigenvalue equation. saying that TV is equal to lambda V. Which in this case would be what? TV now says that we have Z1, whatever I just scrolled past, Z1 plus 3 Z sub 2 is equal to lambda Z1. And what else? Minus Z1 plus 4 Z sub 2 is equal to lambda Z sub 2. And from those relationships, we can find the eigenvalues lambda that solve this, and then we can find our eigenvectors, and also have another way of creating eigenvalue and eigenvector relationships from this eigenvalue eigenvector equation. Now, if we do want to start talking about inverses and inverses in general, which you might in many different environments, now I'm actually moving beyond chapter 10 or our first book. Now I'm sort of stepping out based on what we've talked about this semester. We now are fully ready and capable of doing a lot of different linear algebra ideas or concepts. Suppose we talk about a way of pseudo-inverting a linear map. Not a linear operator necessarily, but a linear map. And that's the Moore-Penrose pseudo-inverse. And how can we maybe put that in context? Suppose you have a map and that map could correspond to a measurement system. Or could be a measurement system. So that now you are taking this linear map from an input vector space U to an output vector space V. Or in terms of specific vectors, you could think of this as potentially M as our measurement. That's a measurement vector is equal to a linear map applied to some unknown vector W of variables. Where here, W is our vector in our input vector space U, and let's say that that's a finite dimensional vector space of dimension capital N, Nevada, and let's say that M, our output vector space, is an element of V, or M is a vector in our output vector space V, and let's just for generality, let's assume that that's a finite dimensional vector space of dimension capital M, or Michigan. So that now you have a system that you're maybe collecting measurement data from. And you're now collecting these vectors M, and you know that what you're measuring is now linearly related to some other vector in the underlying system. So you now have M is equal to TW. What we want to do, or we wish, to use the output vector M to infer or learn something about W. So we wish to use the output vector M to infer something about the input vector W. Here's a question. What is the best linear method for estimating our input vector W from the measurement vector or output vector N? And let's go ahead and create a variable for that. Let's say that we'll call W hat our estimate. That's what we'll define to be our estimate of the true input vector W. And actually the answer depends. It depends on our system, it depends on the dimension of our input vector, it depends on the dimension of our output vector, but let's just look at one answer. Suppose we say answer 1. Suppose that our input vector space is the same as our output vector space, and suppose that our linear map, T, which is now a linear operator on U, suppose it's now full rank. What do we mean by full rank? If I took the determinant of T, what would I get? Would I get 0? You have no 0 eigenvalues, do you? You would get a non-zero value for the determinant of this linear operator. You now know that you have what? An injective operator, you have a surjective operator, and it's invertible. So if U is equal to V and our linear operator is full rank, then the best estimate which is our W hat, is in fact exact. Meaning, now if our linear operator is full rank, then we can simply invert it. And we would simply find our estimate, W hat, by applying the inverse of that linear map to the output measurement vector N. In this case, M was TW, and so now we've shown that in fact it is an exact estimate. W hat is W, the original input vector. That's the cleanest answer. The other answers are a little more interesting. Answer 2. Suppose that we still have the input vector space equal to the output vector space, but now let's suppose that T, which is our linear operator on V or U, is not full rank. What kind of picture can we draw for that? Clouds? What are we meaning if it's not full rank? Well, now we could say that all the points here might map through this linear map T to the same exact point, where we might have all vectors in U, which is equal to V, and here V is equal to U, we still might have those vectors all mapping into a single point. Or another way to think of this is T is many to one. There's many input vectors that map to one output vector. What does that say? That says that T is non-injective. And remember our relationship, or this theorem relating to inverses, injectivity, and surjectivity. We have no inverse, and it's non-surjective. Where here we have many vectors that map to the same vector. Or we have a non-trivial null space. So that might now lead to the following question, question prime, or Q prime. Which of many estimates, possible W hats, should we pick? Since now there's all sorts of W hats that might lead to the same M. This is many to one. An answer to that primed question now is A prime, is we might want to pick the estimate, pick W hat, that has the smallest norm. That might be one way of picking that. Pick the W hat with the minimum norm. In that case, we actually are looking at an operator, but we could have the same kind of thinking for a linear map, where the input and output vector spaces may not be the same in dimension. Or the same thing happens if M is less than N. This is explicitly the many to one condition. And then it's obvious, I hope, that it's non-invertible. Or in fact, it's underdetermined. We have fewer outputs than we have input coordinates. Or if we wanted to think about it, our matrix representation now looks like that. It's now short and wide. M, which is this dimension, is less than N, which is the number of columns in our matrix. Which in this case we have our non-trivial null space. It's many to one. There's all sorts of vectors maybe in the input space that lead to the same output vector. But again, we might want to seek the W hat that's the minimum norm solution. Again, seek to find the minimum norm solution. We can also look at the other case. Suppose we have more coordinates in our output vector m than we have in the input vector w. So now what if capital M is bigger than capital N? Then the system is overdetermined. So a unique solution should or could exist. But the matrix representation of T is again not square. Or again, how do you find the inverse? In this case, what's the matrix representation of T look like in terms of a rectangle? It's now tall and narrow, isn't it? The other case was short and wide. This is now tall and narrow, and we would like to know, is there any way to find an estimate for the input vector given these output measurements in? We can actually put all of these together. So we have three different scenarios. We have one scenario where we have an operator. The input vector space and the output vector space are the same. So our matrix representation would be square, but we were told that it's non-injective, non-surjective, so it doesn't have an inverse. Another case is where it's underdetermined. We have a short and wide matrix representation of this linear operator. And the third case is we might have it overdetermined, and we now have more measurements than we have coordinates in our input vector. All of these situations can be addressed by finding what we'll call a reconstruction operator let's call it P, that minimizes an error. And that error now is the error defined to be the linear operator T applied to our estimate W hat minus the output vector M squared. And what's another way of writing that? So we could write that as TW hat inner product of TW hat minus M with itself. We can now write that as these four inner products by pushing that out. We can move the linear operator around in the slot by using the adjoint, and then to find the minimum with respect to what? With respect to W hat, that's what we're trying to pick W hat from. We can now find the partial of E with respect to W hat, and that will actually end up being 2 times T dagger, or the adjoint of T, times the quantity T W hat minus M. And at the minimum, we want that to equal 0. That's now going back to our calculus. So we won't show that, but now that we have this relationship between the linear map W hat and the measurement M, can we find a way of computing W hat from this equation that solves this equation? This will now minimize that error, or 2 we can divide out. That's, we're not dividing by 0, we're just dividing by 2. And we can then end up with this equation, T dagger T W hat minus T dagger M is equal to 0. Or T dagger T W hat is equal to T dagger M. And now what do we know about T dagger T dimensionally? It's square. So now we can, if it has an inverse, and we'll talk about what we would do if it does not, but if it has an inverse, we can invert that, and we now have an estimate for our input vector W, and we've been calling that W hat. So that now we have T dagger T inverted times T dagger times our output vector M, and this now on the left of M is our reconstruction operator, or P, and that's now this T dagger T inverse T dagger, and that's the Moore-Penrose pseudo-inverse. Where this particular claim to fame person is that Penrose, Roger Penrose, the physicist that we've put in the class resources, The Road to Reality, where those chapters are now talking about numbers and complex numbers, etc. But he now has his name connected to many things, but one is this pseudo-inverse operation. Let's look at what that maybe gives us, this pseudo-inverse. If T dagger T is not invertible, we know it's always square. What else do we know about T dagger T? It's non-negative, isn't it? So it's what we were calling a positive operator. It's non-negative, so the worst we can do is have 0 eigenvalues. We're not going to have negative eigenvalues. It can actually be shown, so this is now non-negative or positive. We can show that P equaling the limit as epsilon gets small or goes to 0 of T dagger T plus epsilon I. So now we're adding in a small invertible piece to T dagger T. We can now say that T dagger T plus epsilon I, the inverse of that times T dagger, is going to be our pseudo-inverse P. This matrix always exists, and it also minimizes the error. Meaning if it indeed does have 0 eigenvalues, we can add in a small strictly positive operator, epsilon I, invert that, which would allow us to invert that matrix in parentheses, or that operator in parentheses, and pre-multiply that by T dagger. And then we have our reconstruction operator. We can also create this pseudo-inverse using the singular value decomposition. P can be easily obtained from the singular value decomposition. Meaning, if we have this linear operator T, we can find the singular value decomposition of its matrix representation. Here I'm just going to say T is equal to U, S, V transpose. If we can find U, S, and V, maybe I shouldn't have used S there. S is, maybe I will change that because you're going to think that's this isometry. It's not. Let me call it sigma. U sigma V transpose. Then P is equal to V, let's say sigma tilde U transpose. Where now if I have sigma is equal to diagonal of sigma sub I, where sigma sub i's are my singular values of that linear operator T, then sigma tilde is going to be this diagonal matrix that inverts those if they are non-zero. And I just assign them to be 0 for sigma sub I equal to 0. And in fact, if you wanted to do this maybe a little bit more numerically in a nice way, maybe you wanted to say if those singular values are tiny, less than some numerical epsilon, I'm going to set them to 0 also. So now you can find this pseudo-inverse from the singular value decomposition. Yes? Well, that's why the question was, what if we have very tiny singular values? Then we're going to really be exploding along the diagonal of sigma tilde. And what I'm saying, maybe for nice behavior in this sigma tilde, you might just establish a numerical precision or an epsilon and say if sigma gets less than epsilon, let's say 10 to the minus 6, we're going to set those equal to 0 and not divide by that 10 to the minus 6. So we will now just say that's 0, and we're annihilating that, the information coming to us from that direction and going out in the other direction relative to these orthonormal basis vectors related to V and U. So we're just annihilating the information coming in and going out in those particular directions by setting, because the singular value is very small, it's saying you don't know a whole lot about that particular information coming in and going out in those directions. So here you would just say, let's just set them equal to 0 for numerical niceness. Another note is if, in fact, T is invertible, what happens to this reconstruction operator? P, we said, was T dagger T inverted times T dagger. But now if T is invertible, then T dagger is invertible, and we can now say that we have T inverse times T dagger inverse. Remember, we've switched the order of a product being inverted, and now that's times T dagger. The right two pieces, though, are just the inverse of each other. Those are now the identity, so that we now have T inverse times the identity, and that's just T inverse. So this reconstruction operator works if T is invertible. It just produces T inverse. It gives you the T inverse that you have assumed or are known to have exist. So in all three of these cases, this reconstruction or this pseudo-inverse by Moore-Penrose works. So it works in all cases. Questions on that? So now you have another reason why you might want to use or be comfortable with the singular value decomposition. Now you can invert, essentially, all of these different map relationships, whether it's overdetermined, underdetermined, or it's non-singular. Or, I'm sorry, well, yeah, non-singular or singular, if it was an operator. What about another topic? Principal component analysis. Or PCA. In this scenario, again, we're trying to answer some questions. Here we say, suppose we are given a set of vectors, and now let's call that set of vectors S, in a finite dimensional vector space V, and suppose that those vectors, or I'm sorry, that vector space V is of dimension n. What we want to answer now with respect to this question is, what is the shortest list that can represent a vector x in that set of vectors, capital S. And you're going to like this answer. It depends. It depends on what we have, or what S represents. Depends on S. Let's look at some examples. Suppose that we have our underlying vector space is R2. And suppose that our set of vectors also live in R2. Or now we have two directions, x1 and x2, and now we want to be able to represent any generic vector x. Or if we now have this arbitrary vector x in R2, how big, or what's the dimension we need to represent that vector? or how big of a list, need a list of what dimension in order to describe any arbitrary vector x in this vector space V. And it needs to be two-dimensional, doesn't it? What if, so here our set of vectors S were living in R2 and they were all over the place. What about another scenario? What if we had the following set of S? Suppose that, again, our underlying vector space is R2, but now maybe our set is just the x1 axis. Meaning all of the vectors that are in our set S lie in the x direction. So that now we have x there. What do we need in order to describe that? Or how many vectors in our list? Do we need two vectors? No, we just need the one, don't we? Need only one number or vector, let's say A equal to A0. What if somebody now says that you have the following: x1 and x2, and then they start giving you this list of vectors, and I'm just going to put a dot where the end of that vector would lie. So our set S is full. It has a lot of different vectors. Each of those dots is one of the vectors in S. Our underlying vector space is R2, and S is clustered in what way? Maybe I didn't draw it very well, but you could sort of visualize that, couldn't you? And now how many vectors would you need to describe that list of vectors in S? As long as you know this direction, you just need to know that direction, right? That's just one vector. So you could describe all of these vectors in S, if they're clustered around, let's say clustered around x1 equal x of 2. Now we could potentially just describe those by that one vector, or that one. Now it may have two components, but those components are the same. You're just scaling those to potentially get your result. There may not be a perfect short list. As we said, it depends on S. But what if we are interested in the best short list of some size? Meaning maybe we're playing in a 20-dimensional space, and we say, what's the best three-dimensional set of vectors to describe this 20-dimensional set of vectors, or these vectors in this 20-dimensional space? Are there three directions that are more significant than others? And that's what we're referring to really when we are talking about this principal component. The principal component in this particular case would be that blue line. That's the principal component of all of those points in that collection of vectors in that set S. And it gets more interesting, obviously, when we have something that's maybe 20-dimensional instead of 2-dimensional. More interesting in higher dimensions. I will simply say that I'll try to post something that now goes over that in a little bit more detail, but it starts to show you how you might create this idea or this notion of principal components for principal component analysis based on the tools that we already have in our possession.